Whereas by the time you get up to myoglobin or a 20K dextran, even though the net ultrafiltration rate is 0, the fact that you have this Starling recirculation flow does provide a significant contribution to the overall rate of mass transfer. And that is going to be different in the out to in configuration versus the in to out configuration. And so, yes, this is exactly what you would expect to see if that's the explanation for the results. And I think it is the likely explanation for the results.
Andrew, isn't it expected that it is just the mass transfer convection that is responsible for the clearance? And do you expect that difference is because of what? Because of more mass transferring from the outside in, and why?
Yeah, it's because these membranes are asymmetric and they have a tight layer on the lumen surface and a larger pore size on the shell side. And so when you're flowing in the outside in direction, the myoglobin gets into the membrane very easily. And it actually polarizes inside of the porous structure of the membrane. So you'll actually build up a somewhat higher concentration of myoglobin inside the porous structure of the membrane, which actually creates a large concentration gradient across the skin to drive diffusion in that direction. When the flow's the other direction, the myoglobin actually has a hard time getting into the membrane because the pores are small. And so that phenomena doesn't occur. And so you get less transport in the in to out or conventional direction than you do in the out to in direction.
Which leads me to a question. We're making a membrane that's going to have that smooth, more tight skin on the outside of the fiber for hemocompatibility. Would we lose this advantage with that skin? And I sort of heard through what you said, we probably lose that advantage somewhat.
Yes.
Yeah.
Now you won't drop below the in to out configuration, but you probably won't see this magnitude of a benefit of running out to in terms of the clearance.
Yeah, but I would expect the fouling would be quite different though.
So if this you're exactly right. The explanation I gave was in the absence of fouling, and so if there is fouling going on, and the fouling characteristics are different depending upon whether you're inside out or outside in, that's an added complication. But at least for the dextran data, it's very unlikely that there was any fouling in those experiments to be of significance.
Yeah. So so I think obviously, all these results make sense in PBS when you're doing stuff in blood, because there's DSA in blood, and it's going to start fouling. It's going to start fouling both layers. One layer more so start fouling one of the layers. The more open pore structure more so than the other. The results would end up being different. That's correct. That's the main.
It's a more complicated situation.
It's a more complicated situation, but at least in PBS, this is what is observed. Mm-hmm.
Yeah.
Andrew, didn't you think with the dextran, which is non-adsorptive, that your explanation there will be more accumulation in the porous layer? I believe this may be valid more for myoglobin than dextran. You and I did a lot of dextran work. Dextran is unlikely to accumulate very much in the porous layer.
So it accumulates not because it's absorptive or anything like that. It accumulates simply because it's easy for the dextran to get into that layer because it goes in through very large pores, and it's harder for the dextran to get out because at the exit you have a tighter portion of the membrane. And because of that differential rate of of transport, at the beginning of the experiment, the dextran starts going in, but it has a hard time going out. And so it accumulates. It's not sticking. It's not, it's just that if you could somehow get a probe in there and measure the concentration of dextran in solution, that concentration would actually be higher than the concentration that you are feeding into the module because of this differential rate of transport.
But then that explanation goes that this difference is because of diffusive transport concentration gradient or still convective?
It's a combination of convection and diffusion.
Yeah. This is the idea of if I remember right, this is like some idea of a concentration polarization, right, Andrew? Yeah. So it's essentially you have convection pushing everything to the membrane, right, or to the membrane, and then the idea is that since there's a partial rejection, you have solute accumulating and get a local increase until it increases so much that it'll start back diffusing, right? And so that the thickness is set by the balance between convection and diffusion.
Correct. And when we're talking about a concentration increase, in a situation like this, it's probably only a factor of 2 or maybe 3 increase in concentration. We're not talking about enormous increases in the dextran concentration, but that is enough to cause this type of difference in the clearance in the two directions.
While we are at it, Andrew, also, it is likely we get more fouling if we have that porous layer on the outside because of that porous structure.
Like I said, I doubt the dextrans are doing any significant fouling, but certainly when you're doing experiments with blood, that's going to be an issue.
So having the selective layer on the outside will help us with less fouling, right?
Yes.
All right. Very nice. Proceed, Gigi.
So by the way, one way to sort of it's not a perfect test, but it's a pretty good one. If you're concerned as to whether this is really the right explanation, it is to do the experiments, but with the blood and dialysate solution flowing co-current instead of countercurrent.
Yes.
But when they flow in the same direction and you're at 0 net ultrafiltration, there's very little Starling recirculation flow because that occurs because the pressure gradients are in the opposite directions. Sure. If you flow co-current, that eliminates much of that effect. And so what one would expect to see if you did co-current operation, the clearances will be lower because it's not as good a mass transfer configuration. But you would expect the clearance in the conventional and the outside in to be almost identical when you run co-current compared to, in this case, almost a 30% difference when you're running countercurrent. Now, whether it's really worth the time and effort to do those, extra experiments, that's up to the team to decide. But it is a way to, if you're having difficulty convincing either yourselves or a skeptical reader that this is really the right explanation, if you run co-current, you will eliminate most of that convective flow effect.
Yes.
I see. Yeah, I'm already a believer of the theory. And
Yeah, so like I said, it's like I say, it is a nice way often to demonstrate that really is the explanation, because any of the other phenomena, fouling or something like that, why switching the direction of the flow would make any difference at all? Well, it shouldn't. It won't change any of those things, but it does change the magnitude of the Starling recirculation flow. And so if that is the key factor, it basically washes most of it out. And you would expect, again, the clearances will be lower, but they'll be lower much more in the outside in configuration than in the inside out configuration.
Yeah, Andrew, if you run it counter current, there will be a crossover point between the pressures.
Yes.
Would that really affect the clearance result where that point of crossing is?
So, if you're running with zero net ultrafiltration, the crossover point is very close to the middle of the device.
Yes.
And the only way to really move it is to not be running at zero net ultrafiltration. Obviously, when you run with positive ultrafiltration, you push that crossover point, towards the exit of the device. But then you have, a significant convective contribution, which will actually make this effect probably even more pronounced as opposed to less pronounced. And so, like I say, it's hard to move that point unless you're going to redesign the dialyzer in some
well, using various restrictions, we think we can move that point somewhat. Would that be desirable?
Like I say, if you were running with where you were trying to exploit this to increase the clearance, I could see a point for doing that. But I think once you go and put the size selective layer on the outside, this effect is largely going to go away.
Yes.
And, at that point, if it goes away, once you start adding restrictors, some of the benefits in terms of not clogging fibers, you may start clogging the shell region because the restrictor is causing clots to form and things. So I don't think that's the direction that you probably want to go, although it's not inconceivable.
Yeah, the work that was the guy Juan Bosch and Beat Van Albertini were doing, where they had two dialyzers in series and used like a 15 gauge needle as a restriction between the two to basically do hemodiafiltration with.
Yeah, and like I say, those are interesting, tricks, but I don't think that's the direction that this project is likely.
No. I just, yeah.
Yeah.
All right.
Okay, Gigi.
Mm-hmm.
Yeah.
And I also have some pressure drop data for the clearance experiments. And first, I want to explain a little bit about our lab setups. So for the right-hand side are the inside-out mode, also called the conventional modes. We have the blood from the bottom entering the dialyzer and exit for the tops. And for the outside-in modes, the blood is also entering the mode. We are just flipping the dialyzer. Yeah. Mm-hmm. So for convenience, at the bottom of the dialyzer, the blood enters, we will mark it as x equals 0. And when they exit at the top, x will be equal to 1. And here are for the myoglobin clearance, these are the pressure drops. And the intercepting points are calculated at the 0.574, pretty close to the center. And and pretty much the same case for the outside in, and they are all in this zero net ultrafiltration as Dr. Andrews indicated, Dr. Zydney indicated. Mm-hmm.
Yeah.
And this is the pressure drop for the dash trend 20K, and same case, the intercepts is around the center, so pretty consistent. And I also have the pressure drop data at different time points to make sure they are not clogging. So yeah, and they're pretty consistent, and the pressure are pretty consistent overall the whole clearance experiment. If there are any questions from the NovaFlux side about the pressure drops?
I mean, it does change a little bit, it looks like, outside in, but this could be error, right? I mean, it's like 0.56 to 0.52.
Yeah.
That's probably just an experimental error.
That would be my guess as well.
Yeah.
And some of it often doesn't show up at the midpoint, not because it's actually not occurring at the midpoint, but because there are pressure drops. You're measuring the pressure outside of the device and extrapolating to the pressure inside of the device. And there are pressure drops. They're not very large across the headers coming in and out, and they're not the same geometry on the dialysate side as it is on the blood side. And so those can cause small discrepancies. I don't think it's worth worrying about any of that. The differences are not dramatic. But my guess is if you could actually measure the pressure in the device, they're probably crossing even closer to the midpoint than what you're measuring.
Yeah, Andrew, with the volumetric balancing in a dialysis machine, maybe Tom can explain, would that situation change or it doesn't really matter? Maybe you are familiar with the balancing chambers. Would that affect this result in any way?
I don't really think so.
Okay.
All right, then I'll proceed through to the sieving coefficient data I collected. So yeah, I want to reiterate about the dash trend. We are observing the sieving coefficient for conventional at 0.436, and for the outside in at 0.655. So again, the outside in have a better sieving coefficient than the conventional. And this is the same case for the myoglobin as well. For the Nipro dialyzer, the same coefficient at outside in is 826 compared to 672.
And the reason the sieving coefficient depends on the selective layer?
Yes.
So how do you explain that?
So again, if it has to do with this polarization that occurs inside the filter. We measure the sieving coefficient based on a measurement of the inlet on the feed side and the concentration that comes out on the other side of the membrane. But if you polarize, what the membrane, the selective layer, is seeing is actually a slightly higher concentration. And so unless you account for that, it looks like the sieving coefficient depends upon the direction of the flow.
Yeah.
And that can happen in 5 minutes?
Yep.
Yeah, okay.
Yeah, and that's the exact explanation that Dr. Zydney just said. The sieving properties of the structure is mostly depending on the first layer that is contacting the blood. And at the outside in, the layer contacting the blood will be the supporting layer instead of the skin layers. And I will move on to the next page. So I have a small observation. So we have a dash trend 20K and myoglobin as the materials. And as the sieving coefficients increasing, the clearance increasing, of course. But would there be a relationship, probably not proportional, some kind of relationship between the sieving coefficient and the clearance regarding the materials, or would the materials actually will make a difference?
Yeah, so in its simplest concept, the clearance has contributions from both diffusion and convection, and the sieving coefficient gives you the magnitude of the convective contribution to the clearance. And so, the fact that there's a difference in sieving coefficient does imply that there will be a difference in clearance, because we think that the clearance is partially due to this convective
Convection,
flow, even at zero ultrafiltration, because of this Starling phenomenon. But in order to be more quantitative than that, you would also have to know what the diffusive contribution is.
Right.
Because even if there was no convection, there will be clearance of both the dextran and the myoglobin. You don't expect the clearance to go to zero if you eliminate the convection. And so there are models that try to separate out the convective contribution and the diffusive contribution. So it is possible to do a more extensive analysis of these data. Often it requires, I don't know how accurate you would get with, data at just 0 and 60 ultrafiltration rate, but if you had 0, 20, and 40 and 60, you could probably use some of the available models to fit both the diffusive part and the convective part. Again, it really comes down to what is the study and what you're trying to show in a publication. But there is a relationship, but it's not, you can't just take the sieving coefficient and say, once I know the sieving coefficient, this is what the clearance is, because it is more complicated than that.
Right.
Yeah, Andrew,
And ZG.
Go ahead.
Oh, sorry, go ahead.
Andrew, if we repeat this experiment with a symmetric membrane, these differences would disappear?
They would largely disappear.
Mm-hmm.
Would it be prudent to try it with something like cellulose triacetate membrane and see?
Or
it is not worth doing.
Yeah, like I say, it really comes down to how much is it worth pursuing to try to prove that. It would be nice data to show that the difference almost completely disappears when you go with a symmetric membrane. Whether it's worth the time and the effort, that's.
No, but you know enough. I don't think it is probably worth doing it, at least at this stage.
It probably would not be my top priority experiment, but it's certainly a good it's certainly an appropriate idea to think about. And if somebody has the time at some point to do that experiment, it would be nice data to have. It would certainly help fill in a gap.
Also, Andrew, I have another question about, with these larger molecular size, the diffusive contribution may not be very large because of the size, or what do you estimate?
Clearly if the diffusive contribution were dominating, you wouldn't see a difference between the conventional and the outside in. And so, I agree with you. The data suggests that the diffusive contribution is relatively small, but relatively small and negligible are not the same. Not the same things. It could be that 20 mils per minute is diffusive, or and so it's only half of what you see in the outside in, but it's still 20 mils per minute, and maybe it's only 15 mils per minute. So it's probably not the dominant contribution, but it's probably a meaningful contribution to the overall clearance, if I had to guess.
But if the diffusive is very small, how can the polarization layer affect the convective?
So it has to do with the fact that there is still going to be accumulation because it's easy to get in and it's hard to get out. And that occurs even if diffusion across the membrane is unimportant. In fact, it becomes more pronounced as the diffusive transport gets smaller and smaller because it's the diffusive transport which tends to smear out that concentration buildup. And so the two are really, one is diffusion across the membrane and one is diffusion within the porous structure when you build a concentration gradient. And I don't think you can relate those two, at least not directly.
Right. Okay, ZG.
Yeah.
All right, I
Yeah,
proceed.
so ZG, if you're interested in understanding how to characterize the relationship between clearance and sealing flow, I can share with you some of the papers that involve convection and diffusion. Yeah.
Great.
You'll need to know something about the membrane, the diffusivity inside the membrane, because that's going to be the mass transfer resistance, diffusive mass transfer resistance that dominates.
Right.
And so we'll have to fit that, right? That's the main thing. Because people don't know the top of the head.
That's correct. And there are, as you know, Vic, there are models with varying degrees of complexity. The simplest ones would just require a single parameter that you would fit to the results, and then you could account for both the diffusive and convective contributions. There are more complicated models that can be used, but are again, it's probably just not warranted within the context of this work to try to do anything more than the simple linear type models.
I see. Yes, I think the top priorities of the project will be to simulating the fouling effect, the inside and outside in. So we prepare to, instead of using a new dialyzer for each experiment, we will develop a pre-foul membrane by the BSA solution, and then we can use the pre-foul membrane to do some of the clearance and sealing coefficient experiment with it. And there are a couple of considerations about the fouling the pre-foul membrane. The first one is how the close flow, conventional or outside in, or we can foul the membrane with a static BSA solution, and also the way including the degrees of fouling, which is already which will be affected by the shear stress, also the flow rate of the blood, and also the time, the exposure times. And here, the right-hand side, we have the outside-in hemofiltration paper. And so we can see that when we are having the inside-out hemofiltration, it will start, the pressure, the exhale pressure drop will start to increasing over time from 6 hours to 24 hours. But for the outside-in modes, which is the outside-in closed flows, it didn't build up as quickly or barely changes when we are having the outside-in mode. So I was thinking maybe when we are doing the pre-foul membrane, perhaps we should probably go with the conventional modes so that we can have higher degrees of fouling to the pre-foul membrane.
So the data that's shown here are not the pressure drop across the membrane. It's the pressure drop from the
across the filter
inlet to the blood outlet. And reason that the pressure went up is not what I would usually think of as membrane fouling.
Yes,
but was actually clogging of the fibers,
that's correct.
probably would not happen with BSA, but happens with blood.
Oh, I
because
see.
Yeah,
blood cells, clog and there's thrombus and things like that. So, there you will get membrane fouling, but membrane fouling will have very little effect on the pressure drop between the inlet and outlet, because the thickness of any fouling layer on the membrane is much smaller than the inner diameter of these fibers.
I see.
right.
The questions you ask, though, are good ones, because when the membrane is used in the conventional orientation, most of the fouling is going to be outside of the membrane, because very little BSA is able to cross that selective barrier in these filters. Whereas if you foul from the outside in, you run the risk of depositing a lot of BSA, potentially irreversibly,
In the porous,
within the porous structure of the membrane, because it's going to get in and it's very hard for it to get out. And so, since BSA does tend to stick, you could get a lot of deposition of BSA. And so, if I had to guess, fouling will be much worse in the outside in configuration, but it may not be a realistic type of fouling, because if you ultimately are going to switch to having a selective barrier on the outside of the filter, most of that's going to disappear, because the BSA would then only foul the outside of the membrane instead of the inside of the membrane. So I'm not 100% sure I know, what the best approach is, but I agree with you completely that you want to think it through, because you could easily be studying something that is not ever going to be a realistic phenomena. Like I say, if BSA is getting into the membrane pores and getting stuck inside the pores, you probably could never use that membrane for dialysis or diafiltration in a real process.
Andrew, in order to study the effect of fouling, inside out versus outside in, maybe because we are making that membrane yet, but we don't have it.
Right.
Maybe it would be useful to use a symmetric membrane to see the difference between the two modes.
Yeah. A symmetric membrane would eliminate this large discrepancy in the two directions. And so that is very definitely one approach. Like I say, you could just foul the lumen side and challenge with dextrans, and feel that you're studying the fouled membrane in the two orientations. Yeah. But you're right, it's a little bit odd. You've fouled it in, where there normally won't be blood. So
yeah. So in order to study fouling, what would you recommend the group at Purdue can do on the outside in, or because this is one of the main concerns, even FDA asked us about it. Will the secondary membrane affect the clearance when the outside in different from the inside out? So how can we resolve this dilemma in the experiment?
Yeah, I think the cleanest experiment right now is probably to use a homogeneous membrane, and do the fouling on the inside when you're running in that direction, and do the fouling on the outside when you're running in that direction. If trying to put myself in the position of the FDA, that would be the data that I think I would find most convincing that this is not an issue. Ultimately, you'll have to run with the fibers that you want to use with the selective barrier on the outside surface and show that everything works the way it's supposed to work. But in the short term, I think using a homogeneous membrane may be the cleanest approach.
From your experience, are there any filters, even maybe on the biotechnology side, that they have the selective layer on the outside that we can use? Or
So that I don't believe there are any dialysis membranes, but there are ultrafiltration membranes that have the selective layer on the outside. They're usually used in water treatment applications where they're used in an outside-in configuration.
these are large modules, right?
Right, in large modules, but it doesn't mean that you couldn't get some of those, fibers and try to study them, but they're not dialysis membranes, and they often are much thicker than a dialysis membrane would be, and they may have very different inner diameters, and so I don't know. I'm not sure I would find, as a membrane person, those data would work for me. As an FDA, examiner, I don't think that those data would be that useful.
Yeah. So maybe
I've never been an FDA examiner before, but that would be, I think that they would find data with a cellulose triacetate dialyzer to be much more convincing than something like that.
Because what we wanted to do, Andrew, is that when we flow the blood on the outside, that you would have different relationships with respect to the shear stress and shear rate. That we need to understand that so that in long-term treatment, we won't run into an issue of effect of fouling on clearance, especially convective.
No, I agree completely. I agree completely with the importance of doing those experiments and having that data. And in the absence of the membranes that you'd like to use, I think the homogeneous membranes are probably the best option.
Yeah, I think this would teach us if there is a variance, then we can vary the flow conditions. And see where we are with respect to fouling Tom. I think maybe some of these experiments should be done, Vivek, with a cellulose triacetate, which these filters exist.
Okay.
Right, Tom?
Is that?
Yeah, still CTA filters, yes, I believe so.
So, are there any specific, membranes that you would like us to look at? Are there any ones that you want to send over? That we can.
Nipro, I think are really the only ones.
Is there anyone that's still making the cellulose triacetate, Tom?
Nipro is still making and selling.
Okay. Andrew, you're not doing too much dialysis now, I presume.
No, we're not, and so I don't have any membranes. Nipro are the ones that we've used most recently, and I don't want to say that there isn't somebody else, but I'm not aware of anybody else.
Were these the triacetate?
Yeah.
Okay.
Yeah.
Maybe we can procure some of them, Tom, and try that, because the fouling is the next step. Until we get our outside-in filter, will be an outside-in, we can learn a great deal from a homogeneous membrane. You agree?
Yeah, sure.
I think so.
Yeah, so the main idea is you want to look at, you want to do homogeneous membranes, look at the fouling on both sides, try to understand the fouling characteristics on both sides. And then,
Correct.
That's the main thing. And then understand how that alters the clearance if it does.
If it
Most
does.
likely it will. Yeah. Mm-hmm.
And
Okay.
actually, Andrew, it will give us actually some ideas about the effect of shear stress or shear rate on the two modes, because we may be able to manipulate that by, for example, what is the, if you think about the lattice model as we had in the paper, how far the fibers should be away from each other to get you what you want, so
Sure.
that you can dialyze a patient under the similar flow conditions, I presume.
Yep, I would agree.
And I have a question. So with this matter, do we consider the exposure of time to the fouling as a parameters of the degrees of fouling as well in this case? Or do we just use a much longer time to ensure it's fouled completely or to a certain levels of fouling?
Yeah, I mean, I think you want to standardize the fouling conditions. You're really looking, you if anything, you don't want to foul to completely unrealistic levels, but you'd like to do a significant amount of fouling so that if there is a difference, you'll be able to pick it up in the experiments. So you were proposing 6% BSA for 4 hours. That doesn't seem unreasonable to me as a pretty robust and extensive fouling. If I wouldn't go for a week, because that's just not likely to be the most realistic set of conditions. But 4 hours with a high BSA concentration, that to me seems like a.
But Andrew, if this filter is going to be used in acute, where
it could be very long. Yep.
Yeah.
But it's not. If you're recirculating the BSA, that's not quite the same as
Hemofiltration.
pumping blood that is not sitting out on a counter, but is in a patient for long periods of time. So for these experiments, I would consider this to be an appropriate fouling model.
And should we simulate the practical use, which is during the hemofiltration, or should we just circulating the BSA alone again and again? Would the practical mode makes more sense to you if you're running 4 hours in the hemofiltration mode, like a blood patient would do in the dialysis?
Well, I mean, hemofiltration is used very little, really, except for in acute.
Oh.
Yeah. I think what Mohammed was trying to show before, or Dr. Habib was trying to show before, hemofiltration will typically clot. The filters will clot before it will in hemodialysis or even hemodiafiltration. So he was trying to show like a worst case situation. A comparison of outside in to see what would happen.
I see.
Andrew, do you have more general comments how you see this project moving?
Yeah, the plan looks very appropriate in terms of the path forward. I do agree that there is some uncertainty as to how to best do the fouling. We tend to see more fouling when there is some convective flow across the membrane, even if it's not in a hemofiltration mode. Even in hemodiafiltration, you tend to see a little bit more fouling than you do in hemodialysis, just because the convection brings the protein to the surface of the filter, and you get some buildup, which can contribute to a little bit more fouling. Normally those differences are not huge, and so I don't know that it's worth trying to work that into, these initial experiments. Like I say, this to me seems like a pretty good starting point, and, you'll know whether there was significant fouling, because if there's significant fouling, the clearance after the fouling should be significantly less than the clearance before fouling. And so if there's no change in clearance, then obviously you didn't really foul the membrane much. And it would be worth rethinking what the fouling protocols are. But assuming that there is a significant drop in the dextran clearance, then you know that you fouled the membrane quite a bit. And you can see whether, if you do exactly the same procedures in the outside-in configuration, that drop in dextran clearance is similar or more pronounced. If it's similar, then I think you're fine. Your argument is going to be that there is going to be fouling. There's always fouling, but it doesn't really matter that you're putting the foulant on the outside versus putting it on the inside. If the data may not show that, and if that's the case, we're going to have to rethink, what could be done to change the fouling behavior. But as an initial experiment, this seems like a good approach. I definitely would measure the clearance of the clean dialyzer before you do the fouling, so that you've got a baseline for that dialyzer. There can be, small dialyzer to dialyzer variability. And at this point, you don't have any data for the cellulose triacetate if this is what you're going to use for these experiments. So, I would definitely take the dialyzer, measure the clearance inside out, measure the clearance outside in. Then I would take that and do the fouling on the inside and measure the clearance inside out. And then you'd have to take a separate fresh dialyzer to foul on the outside in configuration.
And Andrew, cellulose triacetate is a probably low flux, or
it's not
more mid-flux.
It's more mid-flux. These you would expect to see less of a convective contribution because it is mid-flux, but that's the nature of a homogeneous membrane. The reason that you work with these anisotropic membranes is that they have much higher ultrafiltration coefficients, because the resistance is determined primarily by that selective layer, and it's much thinner in an anisotropic or asymmetric membrane.
Yeah, Andrew, you have a lot of experience. Do you think, and this is a subjective question, are we going to run into problems with fouling on the outside based on the configuration, or if we just can match the shear rates or the shear stress, we should be okay in principle?
I think in principle you should be fine. So I would not anticipate that this is going to be an issue, but I agree with you completely that you have to have the data to demonstrate that just saying it's not going to be an issue is not going to be sufficient. But I don't expect that it's going to be an issue. If you that's my guess, but I've guessed wrong on lots of research projects.
No, but this may actually help us a lot in determining the fiber density or the volume fraction, and comets can be a very important design criteria for us, because we don't know where we are really yet. Have you done any work on calculating shear stress from the outside of a hollow fiber, or just the whatever it is known now from the old work by Brenner and others?
Yeah, to be honest, we've never done anything beyond that.
Yeah.
It's never, to be honest, it's never been a question that we had a need to answer.
Yeah, I think Vivek can handle that, I'm sure.
Yeah. Yeah, I mean, I'm sure you can use this like, hexagonal spaced fibers exactly, or you could probably just, if you want, you can estimate a fanning friction factor, right, by looking at pressure drops.
Correct.
Right.
And at least as to get a pretty good approximation, either of those should work.
Yeah.
Beautiful. All right. Andrew, we and all of you, I'm glad that we have you, Andrew. You are certainly authority in that field, and Vivek and TG, you did a good job, really.
The data look great.
Yeah. So maybe Andrew, you can help the team here, advise us on how to get this published eventually. Then.
Absolutely, be happy to.
Sure. And thanks, Andrew, for all your for taking time out of your day to talk to us. I know you're really busy with all your grad students.
Not a problem.
Andrew, how many graduate students do you have?
I've got 13 right now.
And postdoc?
What was that?
How many postdoc?
Only one postdoc at the moment.
So they are really keeping you busy, huh? Do you still have a teaching load as well?
So fortunately, I'm on sabbatical this year. So
you're a lucky guy.
Normally the answer would be yes, but this year I'm enjoying being relieved of that responsibility.
So you're staying still at Penn State?
I've been doing a little bit of traveling.
Okay.
It's with COVID, it was too difficult to relocate. But I went to a conference out in Colorado, and we actually added on a few days and did some sightseeing and took
Right.
vacation. Going up to a conference in next month up in Boston, and so I'm doing some traveling. I'm going to visit some colleagues, but my home base is still Penn State.
All right.
Hey, Dr. Zydney, I have one more question regarding the HPLC with the refractive index detector. So currently, to have the capability to analyze the BSA with the dash trends, so we developed some kind of HPLC facility at Purdue University. So here are the preliminary data of the pure dash trend 20K and the dash trend 10Ks. They are quite poorly dispersed, and I think this data looks pretty good. But one more thing about the refractive index diagram is when they are with the BSA and the dash trends. So here, to simulate the protein concentration in blood, we are using the BSA concentration at 60 gram per liter. And on the contrary, we are using a quite low concentration of the dash trend, and showing in the refractive index diagram here is that the peak for the BSA is really huge compared to the dash trend.
Which is what you would expect.
Yeah, and for the retention time of the BSA is looking at around 13.7 minutes, and the total time of the elution time is 30 minutes. And for the retention time of the dash trend, there are a couple points at 14 minutes, 16 minutes, and 17 minutes. And the huge peak is at the 17 minutes.
Okay.
Yeah, in order to like further separate the dash trend from BSA and measure the fraction of the dash trend, would you recommend us to use a higher concentration of dash trend? Or would you expect us to use a better separation technology to further separate them in order to
be honest, when we do the experiments, we typically foul the membrane with BSA, but then measure the dextran transport with just dextran.
I see.
So they are hopefully, if you've flushed the filter to remove any BSA that was not strongly adherent to the membrane, that you do the experiment only with dextran, because the reality is it is very difficult by size exclusion to see the dextran when you've got BSA present, unless you were to have, you know, 0.1 gram per liter of BSA and, you know, 2 or 3 grams per liter of dextran. And why would you run that? You know, having that low a BSA concentration isn't particularly meaningful in any way. If you really want to separate the two, what you actually want to do is use an ion exchange column, because you can remove the BSA by an ion exchanger, but then you would take the outflow and have to analyze that by the size exclusion column, because the ion exchange column won't allow you to see the dextran molecular weight distribution at all, because it doesn't separate on the basis of molecular weight. So you could, if you needed to do experiments this way, you would typically, you know, find a positively charged ion exchanger, a Q resin. You'd run the BSA through, all the BSA would stick, and you'd end up with a sample that is only dextran that comes out of the column. And then you would take that and run it through a second HPLC using the aquagel column.
I see.
Again, it could be done, but we never do that. We foul with the BSA, and then we just do pure dextran as our challenge, and that eliminates the problem, because you can just analyze the dextrans.
Right. Yeah. That makes more sense. Yeah. Thank you so much for the input. Yeah. That's
Sure.
really helpful.
Sure.
Okay, I think, thank you all. I think this was fantastic, Andrew and everyone else.
Yeah, thanks a lot, Andrew.
Vivek and
Thank you.
Gigi, you guys are doing very well on time.
Yep. Keep up the
Have a
work.
good day, all of you. Thank
Yes.
you. Have a good
Have a great
weekend.
Good weekend.
Again,
Good
Andrew,
weekend.
really appreciate it.
Yeah. Appreciate
You're
the
welcome.
help, Dr.
Bye-bye.
Andrew.
Thank you.